Dear students, today we will talk about elastic constants and the relation between them. Now we know that whenever we apply forces on a body, these bodies get deformed to a certain extent, right? All those deformations can be expressed in various ways. It depends whether the volume of the body has changed or it has not changed, whether the length of the body has changed or it has not changed, or whether the body has bent through certain angle or it has not bent, right? So we define elastic constants in those different ways. Now suppose when we apply a force on a body and its length increases or decreases, then if delta L is the change in the length and L is the original length, then the ratio of the two is called as longitudinal strain. So longitudinal strain is the ratio of change in length and original length once a force F is applied per unit area of the body. So this force per unit area is expressed as stress. You know that. Similarly, if the force is such that it changes the volume of the body, suppose delta V is the change in volume and V is the original volume, then the ratio of the two, that is delta V by V, is called volumetric strain. And again, the force that we have applied per unit area is called stress. That's force per unit area. We have applied force per unit area of the body from any of its faces, any of its sides, right? Or it may so happen that the body may bend through certain angle. It may bend through certain angle. Suppose it bends through certain angle, say this, say this. So this angle is called as angle of shear. Angle of shear or shear strain. And it is simply represented by theta. Now we define elastic constants. The first constant is Young's modulus Y. It is defined in case the body suffers a deformation only along its length. So Young's modulus is stress or longitudinal stress by longitudinal strain. Longitudinal strain. And what is longitudinal stress? It is force per unit area. And what is longitudinal strain? It is change in length by original length. Similarly, we define another elastic constant, that is K. This is called as bulk modulus. Remember, this is called as Young's modulus and this is called as bulk modulus. This is given by stress by volumetric strain, because in this case the volume of the body is changing. So stress is again force per unit area and volumetric strain is change in volume by original volume. Similarly, we define another constant, that is eta or neta. This is called modulus of rigidity. Modulus of rigidity. So this is equal to stress by angle of shear, that is theta. And what is that? Force per unit area by theta, or it can be better expressed as F by A theta simply. So this is called as modulus of rigidity. Now we define another parameter, that is called as sigma, that is Poisson's ratio. Poisson's ratio. But before that, you need to understand, suppose we have a metallic rod or a cylinder whose cross section is circular, or it can also be square type or rectangular type, but let us choose a circular cross section for example. Then when we apply force on the body to stretch it, remember its length increases and that is called as longitudinal strain, but its width or its area of cross section, it decreases. So that's a common experience. Whenever you stretch the wires, their lengths increase but their diameters decrease. By stretching, they begin to also thin. The wires also thin. They get thinned when we apply force on them. That means their diameters shrink but their lengths increase. So this change in length to original length is denoted by alpha, and this change in diameter to original diameter is denoted by another parameter beta. This is called as longitudinal strain, that you have already read, longitudinal strain, and this is called as lateral strain. The only difference is that this change is produced along the direction of force and this change is produced perpendicular to the direction of force, because this diameter is perpendicular to the direction of force. So the ratio beta by alpha, that is the ratio of lateral strain by longitudinal strain, is determined or given by another constant that's called sigma. This is called as Poisson's ratio. Now if you understand all these things very well, then it is very easy for you to establish the relation between these four constants, four elastic constants. Now what are the four elastic constants? Young's modulus y, bulk modulus k, modulus of rigidity neta, and Poisson's ratio sigma. But remember, we can connect either y, k and sigma or y, neta and sigma. And why is it so? Because this is the case which arises when the volume of the body changes on the application of force. When the volume of the body changes. And in case the volume doesn't change, if the volume remains same, then we can establish a relation between Young's modulus, modulus of rigidity, and Poisson's ratio. This k, that is bulk modulus, is involved only when volume of the body is changed. And if this k constant is not involved, then the volume of the body doesn't change. So practically also we can only have two cases, that by applying the force the volume of the body changes or it does not change. In this case we can connect these three, and in this case we can connect these three. Now let's do that. Suppose you have a cube of unit length, breadth and height, that is Lx is 1, Ly is 1, Lz is 1. So what is volume? Volume is also 1. So suppose it is a unit meter or unit centimeter, so it is unit meter or unit centimeter or whatever. So the volume is also 1 meter cube or 1 centimeter cube. Similarly, the area of each face, that is also 1 meter square or 1 centimeter square, right? Now let us see what happens to the body when we start applying forces on it. Again we choose to apply a force of unit only, unit magnitude only. So F is also equal to 1, whether it be 1 dyne or 1 Newton, but it is 1, right? Now let us see what happens to the three lengths Lx, Ly and Lz. And remember, we are applying forces on all the 6 faces one by one. Firstly, we apply in the x direction, that is on this and this face. Then we apply in the y direction, that is on this and this face. And then we apply in the z direction, that is on this and this face, right? Now, you remember that whenever the lengths are stretched, the change in length is expressed in terms of alpha, right? And the change in length perpendicular to the direction of force is expressed in terms of beta. So Lx dash will be Lx dash. This is the new length once the force has been applied, the force of unit magnitude, right? So this Lx dash is Lx plus alpha, because now it gets elongated along the direction. But it also gets compressed by a factor beta along other two directions. So it will be Lx plus alpha minus beta minus beta. I hope all of you remember that. So I am going to repeat this expression again, that once you apply the force in the x direction, what do we expect for the length along Lx? We know that it will stretch by a parameter alpha. Alpha is the longitudinal strain. But once we apply the same force on the other two pair of faces, this will decrease by an amount beta and by an amount beta. I hope you understand that. And Lx is originally 1 because we have chosen a cube of unit length, unit breadth, unit height, right? So Lx is 1, so it is plus alpha minus 2 beta. Remember that by the application, I'm repeating it again, that by the application of forces, each length will get elongated along one direction, but it will get contracted along the other two directions on account of the forces that we have applied on the other faces. So the elongation will be represented by alpha, but the contraction along the other two faces will be represented by beta, right? So Lx dash will be 1 plus alpha minus 2 beta. Similarly, Ly dash will be 1 plus alpha minus 2 beta, and Lz dash will also be 1 plus alpha minus 2 beta. So if the original volume was 1, what is the new volume? V dash. So that is this into this into this. So it is 1 plus alpha minus 2 beta, right? Cube. So V dash is equal to, once we use binomial theorem to expand it, we know that power comes down and the higher powers are neglected because alpha and beta are very small terms. So we write it as 1 plus 3 alpha minus 6 beta, because I have multiplied with this power to these coefficients, right? Now, what is the change in volume? The change in volume is obviously the new volume minus the original volume. And what is the new volume? That is this 1 plus 3 alpha minus 6 beta. So it is 1 plus 3 alpha minus 6 beta. And what is the original volume? We know that is 1 because we have chosen a cube of unit dimension. So this 1 and 1 will go. We are left with 3 alpha minus 6 beta only. So this 3 will be taken as common. This is alpha minus 2 beta. Now let us go back to the original equations, original definitions. How did you define this bulk modulus? You said that it is stress by volumetric strain. So it is force per unit area delta V by V. We know in this case we have chosen a force of unit magnitude. Area is also 1, volume is also 1. So this expression reduces to 1 by delta V only, right? So this implies that K bulk modulus is actually 1 by delta V. So this K is, what is delta V? It is 3 alpha minus 2 beta. Now let us divide the numerator and denominator by alpha. 1 by alpha divided by 3 times alpha by alpha is 1 and 2 times beta by alpha. All I have done is that I have divided the numerator and denominator by alpha. So this is what I obtained. Now I have already said that this beta by alpha is how much? Sigma. So for this beta by alpha, I can write sigma 1 by alpha by 3 times 1 minus 2 sigma. Sigma is the Poisson's ratio. Now let us go back to the definitions with which we had started. What is this Young's modulus? Again, if we go by the definition, what we have done in this, that force is of unit magnitude, area is again unity, length is again unity. So this is basically 1 by delta L, right? And what is this delta L? Remember, if length is unity, delta L is alpha. If length is unity, which is the present case, we have chosen a cube of unit magnitude. So if L is 1, delta L is alpha. And what is this? What is this 1 by alpha? Then it is equal to Y, Young's modulus. I hope you have understood that. So this is Young's modulus. Let me not go back to that page again. We have defined Young's modulus, that it is stress, that is force per unit area, by change in length and original length. If all the parameters are unity, because we have a cube of unit dimension, we have a unit area, we have a force of 1 unit magnitude. So this Y is actually 1 by delta L. But all I mean to say is that this delta L is actually equal to alpha because L is 1. So therefore I say that this 1 by alpha is basically Y. So it is 1 by alpha. So it is 1 by alpha. So that is equal to Y. So this is the final relation between Young's modulus, bulk modulus and Poisson's ratio. In the next video, we are going to do the second relation, and that's all. That's all. And you are asked these questions only for the purpose of numerical problems, And these things are actually of much concern, of much usage in the engineering world. That's all. I'm turning these pages one by one again so that you are able to recapitulate it quickly. What did we do? We defined the strain of three types: longitudinal strain, volumetric strain, and angle of shear. Then we defined the four constants: Young's modulus, bulk modulus, modulus of rigidity. And then we also defined a fourth constant, that was Poisson's ratio. And then we tried to connect these three or these three. These three can be connected when the volume of the body changes, and these three can be connected when the volume of the body remains the same. Today we have established this relation, and in the subsequent video we will be establishing the relation between these three. So this is what we did. We tried to make it quite easy by choosing every parameter of a unit dimension. Length, breadth and height were all 1, volume was 1, area was also 1, a force of 1 Newton was chosen, and then we defined that the new length after the application of force would be like this, because it will suffer elongation along one direction but stretching, compression along other two directions. So it was 1 plus alpha minus 2 beta in all the three cases. Then we multiplied the 3 to obtain the new volume. From this new volume we subtracted the older volume, original volume, to get the change in volume, and then we proceeded in this manner to establish this relation. I believe that this is the simplest technique, simpler than what you find in the books. So that's all.